Over to you.
Yeah, thank you. So yeah, this is joint work with Manuel Meitinger and our advisor, Georg Moser. And yeah, this is about resource analysis, which is a fundamental problem because it can be used to understand the efficiency of algorithms and programs, and therefore also help to optimize them. And for example, it can also be used to identify bugs. And there are different static analysis techniques that have been developed already, which can analyze the source code of a program and then fully automatically derive the complexity bounds. However, these static analysis methods are in general not complete, which means, because this is a difficult problem, undesirable problem, which means that they may not be able to derive complexity bounds and just return unknown. And these unknowns are exactly the motivation for our work, which tries to give an answer to the question, what should we do when automation fails? And an alternative approach would be a statistical approach, which basically means to run the program on different inputs, measure the costs, and then infer the complexity based on these observations. And in our work, we have implemented this idea for term rewrite systems and have compared the results to known results on a large benchmark collection of examples. Okay, so first, maybe I should define or clarify what runtime complexity of a term rewrite system is. And I would like to do this on this example, which will be a running example throughout this talk, which is a term rewrite system that encodes multiplication and addition of natural numbers. We have these four function symbols with the corresponding arity, and we have 6 rewrite rules. And in this term rewrite system, for example, we could compute the product of 2 times 3, where we represent these numbers using the successor function. For example, the 2 is successor of 0 times, similar for the number 3. I just will abbreviate this on this slide and put the number of successors as superscript. And now on this term, we can apply the rules, whichever match to this term. In this case, it's only rule 1 that can be applied, and we can rewrite the term to 2 times 2 plus 2. And for this term, again, we have now 2 options. We could use either rule 1 to rewrite the inner product, or we could use rule 5 to rewrite this addition. And if we, in this case, choose to apply rule 1, we would get this term and so on and so forth. So at some point here, we will reach the normal form, which is the number 6, which is the result of 2 times 3. And since no other rule can be applied at this point, this is what we call the normal form. And what's also important to know here is that the initial term was a basic term, which means that it has as root symbol, which is the product, which is a defined symbol, which means that it occurs at the root position of some left-hand side of a rule. The product and the plus symbol are both defined symbols, and the others, which do not occur at a root position of some left-hand side of a rule, are called constructors. And so now we have seen that we could rewrite this initial term 2 times 3 in 10 steps, in this case, to the result number 6. However, we have seen that we have had at some point the possibility to decide between 2 rules. And this leads us to the notion of the derivation height, which is basically, given a term, we ask what is the maximum number of steps we can take from this term, a starting term, where we then reach a normal form. In this case, we know already we have an example where we needed 10 steps, but there could be other derivations that require more steps. So we just can say for the moment it's at least 10. And this number of steps is what we also interpret as cost. And the runtime complexity of a term rewrite system then is given a maximum input size. It's the question, what's the maximum number of steps we can take starting from a basic term, which is not is of size smaller n in this term rewrite system. And for this term rewrite system I've shown you, we know, for example, that the size of the term 2 times 3 is 8, because we have the product at root position, then 2 successor function symbols on the left-hand side, 3 on the right-hand side. That would be in total 6, and the 2 constructor 0, which would be then 8. And 8 would be the size of this term. And an interesting question to ask here, what is then the runtime complexity for the term rewrite system up to size n? And here again, we just can say for the moment, it's at least 10. So we have an example where we need 10 steps, and the term is of size smaller equal than 8. But there could be other terms that require more steps. And we are interested exactly in this function that gives us an upper bound to the number of steps we need to apply for a given term. And we are especially particularly interested in the asymptotic growth of this function. So is it linear, constant, quadratic, or exponential? So how do we get the data where we can then infer the complexity? This is what we call this worst case input computation, where we distinguish in a term rewrite system, which this is the same one as before, we distinguish between simple and complex rules. And simple rules are those that do not contain any defined symbol on the right-hand side, or where the left-hand side is just a constructor. And otherwise, the rules are complex. So in this term rewrite system, the rule 1, 3, and 5 would be complex because we have defined symbols on the right-hand side, and the rules 2, 4, and 6 are what we call simple rules because we have on the right-hand side only constructors or variables. And what we do then is just to combine complex with simple rules to create new rules, which basically are derivations of terms. And we do this by narrowing, which basically means that if we can find a subterm of a given term S that matches some left-hand side of a rule in our TRS with some unification, then we can replace in this term this subterm with the right-hand side. I can give here an example what this means to illustrate it. So we use this narrowing to combine simple with complex rules. So assume we have here the complex rule from our TRS and the simple rule, the rule number 6. So we can combine these rules because as you can see, we can unify the right-hand side of the complex rule with the left-hand side of the simple rule. And right, so this, of course, requires then unification, which requires to rename apart the variables. But then we can give a replacement. So if we substitute here x, variable x with x times y, and here variable x with 0, then we can unify these two terms and create and combine these rules to create a new one. which would be, in this case, the rule going from 0 times successor of a variable y, goes in 2 reduction steps to 0 times y. Right, and we exploit then this idea to create our data, basically. So we start with our term rewrite systems, where we have all the rules. We have the 3 complex rules, and then the 3, I mixed it up now. We have complex and simple rules, where we have cost of 1 for all of them, because they are in the initial term rewrite system. And then we combine the rules, complex with simple rules, and do this as long as we can, or as long as we reach a timeout. And this now creates our data, basically, our measurements, our observations. And based on these rules that we create, we then infer the complexity. And here I have to note that the way we designed this approach, that we combine simple rules with complex rules, means that we can only, that it is designed for terms that lead to some value, because we always have a value at the right-hand side of the simple rule. And therefore, this method, it can be applied to any term rewrite system, but it is designed for term rewrite system that actually produce values, so that correspond to functional programs. So yeah, the last part, how do we estimate the complexity given these new rules? Yeah, we can just read out the costs and the size for each rules that we have generated. For example, we have this rule from the TRS, which rewrites the left-hand side in 1 step to the right-hand side. So, and at the root position, we have the product. So we would have now a measurement, what we call a rule-induced measurement of the product function, where the input size is 4 and the cost is 1. So this would now be one example of a measurement that we can extract then from these rules. And we can do this for all the rules that we have created. And so we see that we have 2 different function symbols, the defined symbols, input size and the cost. So if we plot this, then this would look like that for the specific TRS I've shown. So there we already see by visual inspection that, for example, the plus function seems to have linear growth. But to estimate the complexity from these data points, we first need to take out only the interesting points, which means we only filter those points that have maximum cost for each input size, and only take those where we keep growing throughout the sequence. So as soon as we would decrease with the cost, the angle would decrease to the next point, then we stop. So in this case, only these red dots up to size 20 would remain, because here afterwards we would again decrease. Right, and on this data we then apply or try to infer the asymptotic complexity. But the problem here is that we could just try to fit a polynomial through these points, but the problem is that we can fit them arbitrarily well. So just increasing the complexity of our function gives us always better results. So here you see an example. I think you cannot read it, but this would be a function of a polynomial of degree 2, this polynomial of degree 3, and this a polynomial of degree 4. And the loss of this fitting is, of course, the best with the polynomial of degree 4. So it's not trivial to find the right degree for a function. And the residual sum of squares is not a good indicator for that. But there's this paper by McGeo and Cohen, which says how to find the big O in your data set. And they there present a method based on polynomial interpolation. and this heuristic, which they call difference rule heuristic, and which is also the rule that we then use in our tool. Maybe just to give an idea, there's this theorem, Lagrange interpolation theorem, that says that if you have n plus n 1 points, then there is a unique polynomial of degree at most n, such that it goes through all the points. So it matches them exactly at each position. And so you can use basically this theorem to infer the degree of your data points, because this gives you also an algorithm how to compute the coefficients. And you can do that with the divided difference scheme, which I will sketch here only. So basically, you can construct with the divided difference table. This can be seen as a discrete differentiation of your data set, where, for example, you have in the first column, you have the initial data points, which can be quadratic. Then the second column would correspond to the first differentiation, and the second one to the third one. So if you have an initially a quadratic function, then within the first differentiation step, it would be linear, and then it would be constant. And this is exactly the idea that we can use here. When we see then that a function that our data points are constant, then right, and this is exactly the example of a divided difference table for a quadratic function. We see that applying this scheme, then at degree 2, it gets constant. So this tells us now that the function was of the degree 2, which is exactly here, x squared are the values in the first column. Right, so we can apply this scheme to the data points we collected by narrowing. So this would be the table we have for the plus function. Sorry, there's a typo in the table. It should be a plus. This mouse here. And so we see that it gets constant at k equals 1, which tells us that the function is linear. And similar, we can do this for the multiplication. And here, of course, you see an example now where we have some noise. And this is exactly the problem, because our data set that we have, the data points, do not exactly follow a polynomial of degree 2, but because we have some noise in there. And therefore, in this heuristic that they presented in the paper, they say, we do not check the column where we have then constant values, which would be 7 in this case. So this would then be degree 7, but we do take the column where the values appear to be non-increasing. And this would be here the case for column number 3, which tells us that the degree of this function is 3. So yeah, we validated this method on this large collection of examples, which is used in the termination competition, which consists of over 900 term rewrite systems, for which, or most of them, the bounds on complexity are known from static analysis tools. And so we compared our method or our results, our predictions, with one of the best solver in this benchmark. And we set a timer of 3 seconds to our method. And here I show first the result for not for all, the whole benchmark, but only for those term rewrite systems that correspond basically to functional programs, where we see that only 7 of these examples are unsound, where we basically violate the lower bound of known results, and the remaining 100, the remaining part, there we are compliant, or we have seen that the term rewrite system do not produce any values. And we also could give a result for term rewrite systems where the exact complexity is not known yet, or was not computable with static analysis tools. And we achieved an accuracy here of 75% on the examples where the upper bounds are known. Right, but if we, of course, try to apply this method to the whole benchmark, we see that this decreases the accuracy, and that we have many unsound examples also, just because the method is not intended to be applied to arbitrary term rewrite systems, but it makes more sense, given the construction of the rules we have, to restrict to those that encode functional programs. So, because that's also a limitation of this method, that we may find a timeout, reach the timeout, and since up to that moment we may not have enough inputs collected, which means that if we then try to clean the data and then to infer the complexity, that we just don't have enough data points. Because we have seen before that we need n+1 data points if we want to check whether the complexity is of degree n. So in this case, we would not have enough. Right, so to sum up, we have presented a method for analyzing in a statistical approach the complexity of term rewrite systems that correspond to functional programs. We have shown a technique or reused the technique to estimate the asymptotic complexity, and have validated the approach on known results. And for future work, it could be interesting to integrate maybe also machine learning techniques, because what we do now for the moment is just exhaustive search. We just combine every possible rule, but there could be smarter ways to do that. And also inferring exact polynomials, not just the complexity, not just the asymptotic growth, would be interesting, and maybe also to give guarantees on up to which size we now have we can guarantee the result is correct or not, because we also don't have that for the moment. Okay, and that's it. Thank you for your attention.